Okay. So within our outline, we're on part 3, renal phys. We're now moving on to part C, which is a couple kind of a grab bag of tubules and urine production. Okay. So we left off talking about this idea that, this really kind of goes before this, is that, really what urine is, okay, is a combination of things that were filtered. We talked about the nature of that, freely filtered other than blood cells, white blood cells, formed elements, plasma proteins. And from then on, it was pretty much a non-selective filtration. Okay? So what is filtered minus what is reabsorbed plus what is secreted. Okay? We'll put another diagram up of the glomerulus and the tubular structure here in a bit. Okay? But where we left off was talking about this, how things are a combination of good things or bad things. How the filtrate is. And the good things need to be reabsorbed. The bad things need to be left in the tubule and or removed further by secreting them into the tubule. Okay? So we left off with this kind of idea of this cross-section of the renal tubules, the generalized renal tubule. Reabsorption is pulling stuff out of the filtrate, okay? And secretion is putting stuff back into the filtrate. Okay? So we'll get into down to the cellular level, hopefully today, and look at some of the mechanisms, the pumps and transport mechanisms that cause things to be either reabsorbed or secreted, and it's very specific what will be, which will be done to either, or at any one particular thing. Okay. So we left off on this question of water. So we've gotten to the point of saying, good or bad. Rules game show water. Well, water is normally good. We left off saying, okay. You reabsorb most of it. The number we gave at the beginning was 99% of the water is reabsorbed. That's still in a relatively hydrated person. Okay? If you're dehydrated and you need that water, you can reabsorb 99.99 something. Okay? If you need to. Okay? Now, inevitably, you're going to lose some water. Okay? So you can't avoid that. When you're very dehydrated, you dispose of the toxins and the waste products in fluid. You can't pee out a solid chunk of stuff. Okay? So you're that's never going to be 100% water reabsorption, though it can get very close. Okay. The other thing you have to remember about water is what I'll say a lot. I'll say water follows salt. Okay. And this is the idea of osmosis. Okay. And what this means is we pump salts. And that's generally by pump, I mean something resembling active transport, which it almost always is. Okay. We're going to actively reabsorb salts, for example. And water is going to follow by osmosis. So water, there are no water pumps in the system, okay? So if you pump salt, water follows it. We're going to use that terminology a lot. But let's move on. We already talked about water a little bit. Let's talk about sodium, okay? Good or bad? Both. Depends on your diet. Okay? If you eat a salty diet, it's bad. You have too much of it. You need to get rid of it. Good news. Freely filtered, right? Small, not a protein, not a big plasma protein, not a formed element. So it's going to be freely filtered, okay? And then we just choose to not reabsorb it, right? Well, we can't do that for very long. Remember, we're going to turn over our whole circulation in 25 minutes, so we have to reabsorb it. So you're still talking about something that even when you have too much sodium, might be 95% of it might be reabsorbed, okay? The vast majority of it. It doesn't take long to pee away a lot of salt, sodium specifically, okay? But normally, sodium is rare in nature. People fought wars over salt. Owning the land that had the salt and selling it was a major source of income for civilization. Okay, so salt is still, like a lot of things, is relatively rare in nature. Some places it's plentiful, but in most places, like water, it's actually kind of hard to find. So your body's very good at reabsorbing it when necessary. And as soon as you don't have any, you're going to lose a little bit inevitably. Can't catch every one of them, every single molecule that gets filtered, but you'll catch most of them. Okay. Terms for sodium that you'll use down the road are hyponatremia, we haven't used them already, okay, versus hypernatremia. Okay. So if you have a big old bag of chips and you eat it, your body is now hypernatremic. Okay, so natremia, that's what the Na in sodium stands for in the periodic table. Okay. And if you're low on sodium, that means you got to get some in your diet. Why would you be low in sodium? The kidney's imperfect at retaining it. You'll pee a little bit away eventually, and you need a constant supply in your diet. Again, not necessarily even a day-to-day thing that you'll suffer negative consequences, but you got to get it eventually. Okay? Hydrogen, our old friend. Okay? And when we talk about hydrogen, we can't help but talk about bicarbonate. Okay, so you all know the bicarbonate buffer equation. Hydrogen ion, bicarb ion. Okay, bicarbonate. Is hydrogen a good thing or a bad thing? Normally, what is your urine? Acidic or basic? It's acidic. Okay. That must mean you're disposing of hydrogen, and you are. Okay? Your entire net metabolism normally results in a net balance of hydrogen that must be excreted. Okay? Now, if you eat a vegan diet, you may actually fall on the alkaloid side. You may need hydrogen ions and actually need to get rid of bicarbonate. But your kidney is great at solving either problem. Normally it disposes of hydrogen, but it can also work for an alkalosis versus an acidosis. If you have an acidosis, you have too many hydrogens. Pretty simple, you pee them away. What if you have an alkalosis? You reabsorb them. Does that solve your problem? No, it doesn't actually solve your problem. It just prevents you from not losing more hydrogen. In alkalosis, you don't have enough hydrogen. You're too basic. Okay? So you want to reabsorb those hydrogens, but that doesn't solve your problem. You need to eat acids. Okay? That would be one way. With sodium, that's what we say. If you're low on it, you can try to minimize the loss by reabsorbing a high percentage, but ultimately you need to eat it. And you could eat more acids if you're alkalotic, but the good news is that you can actually secrete bicarb. Okay? Here you're clearly going to secrete hydrogen. Now it turns out, and we'll see this exact mechanism later, okay? When I say secrete bicarb, it's the same thing as saying reabsorb hydrogen. And when I say secrete hydrogen, it's the same thing as saying reabsorb bicarb. Okay? And we'll see this exact mechanism molecularly, how these pumps and secretions and reabsorptions occur later. And it turns out you really can't separate the two. If you're secreting a hydrogen, you're reabsorbing a hydrogen. Sorry, if you're secreting a bicarbonate, you're reabsorbing a hydrogen. And if you're secreting a hydrogen, you're reabsorbing a bicarbonate. And again, we'll get to that later. But it depends on the state you're at, whether you're going to dispose of one versus the other, okay, to get yourself back to normal. Okay. The last category of good or bad, hormones. Are hormones good or bad? Well, you secreted them, you made them, they must be good. But like any system, when you secrete something or when you fire an action potential, you don't want it to last forever. So there's a normal removal mechanism to hormones, which is just kind of built in, okay? And depending on the hormone and the concentration of the hormone secreted originally, that defines, once again, just like the drug example I gave you earlier, that defines the half-life of the hormone, okay? How quickly the kidney gets rid of them. So they're not bad, but there's a natural disposal of them. You don't work really hard to reabsorb most of them. Some of them you do, there's a lot of exceptions to that point, okay? But loss is normal. But the easy part is, hormones are secreted in very low concentration. You're not cranking out a ton of them to get to whatever level you want to be. By definition, they're in the micromolar level usually. So it doesn't take a lot. So if you're peeing a few away, and you need a continuous supply of that hormone to maintain whatever function that hormone is providing, you simply just make a little bit more and keep that level high. Match the rate of elimination with the rate of production, you can have a constant amount. But there's always going to be elimination, okay? Except for what kind of hormones. Which ones are going to be eliminated much slower? The ones that are... Say again? bound to plasma proteins. Okay? The plasma proteins, remember, bind lots of things like thyroid hormone is a recent example. Okay, so those are secreted much more slowly. They have a higher rate of, they have a higher half-life, longer half-life. Okay. Okay, finally in this section, we have urine formation. Just a little reminder of what we're talking about. I just kind of mentioned it early. Urine is what is filtered minus what is secreted, minus what is reabsorbed plus what is secreted, and what's left over is urine. Okay? Just to remind you, urine formation is much, oops, got my arrows directionals backward, much less than GFR. Okay? So glomerular filtration rate. Okay? This is, in the 100 mils per minute. This is in the 1 mil per minute. Okay? So about 1% of what is filtered is actually continues on to be urine, at least as far as the water volume goes. Okay? So very different. Okay? Okay. Before we move on to the tubules themselves, we need to make another general statement about peritubular capillaries. Okay? Remember our diagram? Okay? The simplified tubule system. We have an afferent arteriole coming in. We have the glomerulus. And we have the efferent arteriole coming out. We have a second capillary bed, which is the peritubular capillaries. And then we have an interlobular vein, which would eventually continue to the renal vein. We have the capsule that captured the fluid, and we have the tubule system. And what we talked about is things that are reabsorbed get reabsorbed into the peritubular capillaries. Things that are secreted from the peritubular capillaries and into the tubules. Okay? And we end up at the end with forming urine. Okay? We're going to expand and define all the tubules later in the period. So part D, peritubular capillaries. Remember, these are part of the second series in a portal system. And we want to reabsorb. Remember, 100 mils is going through here. Just think water for a second. Okay? And 99 mils is going to be reabsorbed and passed back into the peritubular capillaries. Okay? So what properties of the peritubular capillaries favor absorption? Okay? Remember Starling's fluid flux. Okay? When we talk about the relative pressure of the capillaries, okay, what's better to absorb fluid, high or low pressure? Low. Very good. Why are they low? Because of resistance, remember? It goes through this first capillary bed and encounters a bunch of resistance. Pressure drops. So what's the pressure in this capillary relative to this capillary bed? Much lower. This one is high, favors filtration outwards. This one low, favors reabsorption inwards, right? Starling's fluid flux, your old friend. Okay? What about the concentration of plasma proteins? What would favor reabsorption? High or low? High, good, good, okay. High, remember, it's like a sponge, and the greater this oncotic force, this osmotic reabsorptive force from the plasma proteins, the better. Why is it high? Because what came out here? Water, plasma, but the plasma proteins got left behind. So if remember, about 20% of the plasma going in gets filtered, okay? So that means there's different math, but about 20% greater concentration of plasma protein in this tube than in this tube, right? They become concentrated because fluid is lost without plasma protein, so it concentrates the plasma protein. They come in here, okay? They're at a relatively high concentration. That favors reabsorption as well, okay? So all this fluid that has to get reabsorbed across this capillary bed, you set up the perfect forces relative to what we talked about earlier last quarter in the Starling's fluid flux equation. Low pressure, high oncotic pressure, great ability to reabsorb all that fluid that needs to get reabsorbed. Okay? Questions? Follow me? Secretion, we're not going to spend as much time on secretion. It's fairly exceptional. Okay? But just don't forget that when I'm secreting something, okay, it's something bad that I need to get rid of, okay? This isn't the way we're going to get rid of sodium if we have too much of it. We're just going to reabsorb less sodium. Secretion in general is either, hydrogen does fall into this category, so we'll talk about that later, okay? But it's the exceptional things. It's the kind of crazy anions or crazy cations. We have special transporters built, and they have to be secreted out of the peritubular capillary, and then there has to be a second transport system that brings them into the tubule. Okay? So just remember the peritubular capillaries are the source of secreted stuff. And this generally falls under the obviously bad things, except for hydrogen, but generally hydrogen's too high, and generally you're secreting it. We'll talk about that later. Okay, part E in this section is hormones. So I've given you a handout to speed things along. What I do normally is I present all the hormones once as a suite of hormones to talk about relative to the kidney. Okay? And then I'll come back as we step through all the different tubules, and I'll talk about how they specifically work. Okay? So on your handout, you've got every hormone that either comes from the kidney or targets the kidney. So some come from the kidney, have nothing to do with the kidney. Some come from the kidney and affect the kidney. Others come from somewhere else and affect the kidney. Okay, but as far as listing endocrine organs in the body, the kidney is one. It produces several hormones. Okay? So what you want to remember is the first one's easy. We've already talked about it. What does EPO stand for? Erythropoietin. Okay? The stimulus that we talked about before is low O2, and its sense, the source and the sensor is kind of in this category, are some cells of the juxtaglomerular apparatus. Okay? Now we're going to talk about that later as a system. Okay? When we talk about regulation, but for now, basically what you should understand about the JGA is that it is found right here. Okay? Kind of a little triangle there, and it interacts with the afferent arteriole, okay, and the glomerulus, okay, and it senses things within the fluid there too, and makes some feedback, and there's some feedback that we'll discuss later. But for right now, this is where specific cells called the mesangial cells of the JGA, we'll put a diagram up later, okay, are what secrete the EPO. So they're sensing this oxygen level, so they're an oxygen sensor. When they sense it's low, they cause a secretion of EPO. EPO goes up. It targets the bone marrow, and what does it cause to happen? More red blood cells, an increased elevated erythropoiesis would be the fancy way of saying it. Okay? Greater red blood cell formation. Now, you might be low on oxygen because your lungs just aren't getting enough, like at altitude, and that might upregulate your hematocrit, okay, which we talked about. Or you might be low on red blood cells because you just hemorrhaged out a liter of blood, and you don't have enough, your lungs are working fine, but you're not carrying enough oxygen. In either case, you'll see replacement of the red blood cells that are lost through hemorrhage, or you'll see an upregulation of hematocrit if you remain at altitude for a long period of time. Okay? So elevated erythropoiesis is the question mark there. Okay. Now we have another one, a number of those. These you might have heard of. A couple of them you've heard of. We'll see what you remember from the ones. You probably haven't talked about renin yet. Okay, renin is secreted also from the JGA, and it's to a separate set of cells called the granular cells. Okay? And the granular cells secrete renin in response to pressure. Okay? Low pressure, low volume. Remember? Pressure reflects a low volume, a dehydrated state. Okay? But that's not all that can affect renin. I did give you a little preview of this story. Okay? If, for example, you have ptosis, descending of the kidney, remember I talked about that the other day, it can cause a constriction, a twisting of the renal arteries going in, and even though your regular central arterial blood pressure may be totally normal, the pressure downstream of that kink might be low. And so people who have ptosis generally see a hypersecretion of renin, and we'll talk about what that causes as we look further down the line. Okay? So It's not an active hormone, though. It turns out it's very different. Okay, the renin-angiotensin system is all in all three of these ones, so it's a more complex system than that. The renin is not actually an active hormone. If you talk about what the target is, the target of it is actually a hormone, not a pre-hormone that resides within the blood called angiotensinogen. Okay, so the diagram that goes along with this is a kind of complex idea. And so what you have to picture with angiotensinogen, remember the complement proteins for clotting, they were sitting out in the bloodstream not doing anything. Okay, they're inactive form. But they got activated and to start the clotting cascade under certain conditions that appropriate for clotting, or inappropriate sometimes. Okay? Angiotensinogen is kind of the same way. So it's sitting out here. And it's going to get converted by renin when it shows up. Okay? So until renin shows up in this low pressure situation, angiotensinogen remains in its inactive form. Okay? It then gets converted to angiotensin 1. So when you try to define hormones as having a target, this is the target of renin. It targets angiotensinogen and converts it to angiotensin 1. Okay? So renin, its only effect really is to cause that conversion to angiotensin 1. Okay? And that's where we end the story. Now we have to talk about angiotensin 1, and I kind of skipped it. I could put another line in the table for angiotensin 1. I chose not to. But now we'll talk about angiotensin 2, which is the active form. Okay? So if renin shows up and angiotensin 1 is now floating around the bloodstream, it will go through some resident enzymes. So these are enzymes that previously weren't doing anything right now. And these are called angiotensin converting enzyme. Ever heard of that? What's the acronym? ACE. ACE blockers. Common drug. We'll talk about that later. For now, let's talk about what it normally does. These are primarily found in the lungs and some other vasculature holds them. But this is sitting around the lungs, and when the angiotensin 1 shows up, it encounters this as it passes through the circulation, and it gets converted to what is now our active hormone, which is angiotensin 2. Okay? So renin really doesn't do anything unto itself other than convert this. Angiotensin 1 doesn't do anything until it encounters the enzyme and then gets converted to this. Angiotensin 2 is our active form. So really, you can simplify the whole story and say that angiotensin 2, the stimulus, is low blood pressure, right? It starts a cascade of events that ultimately results in the active hormone angiotensin 2. Okay? But you can also approach it this way. What's the stimulus? Renin. And where does the store in the bloodstream after conversion from angiotensin 1 by 8? Okay? More importantly, the target here is the proximal tubule. So we've just defined the basic tubules right now at the beginning, okay? And then we'll come back to this and I'll tell you how it works in the proximal tubule next. We'll start in order and we'll do the proximal tubule first. Okay? The general effect is it increases sodium reabsorption. Okay? And we'll talk about how that actually happens. Remember, water follows salt. If I cause increased sodium reabsorption, remember going from the lumen of the tube out back to the body, reabsorption, okay, water's going to follow it. Water follows salt. If I pump salt, I'm going to have water come. So essentially, what am I pumping back into the body? Salt, water, plasma. Okay? Is that a good response to a low blood pressure? Of course it is. Does it solve your low blood volume situation? No, it only retains it. It prevents it from getting worse. Okay? A second effect is so angiotensin 2 has a second effect in this line, it also targets the arteriole. And this is a very general effect of angiotensin 2. It targets all of the arterioles in the body, including the afferent arteriole leading into the glomeruli. And it causes vasoconstriction. Okay? So when we talk about all the arterioles in the body, vasoconstriction leads to what? An increase or decrease in arterial blood pressure? Increase, right? It's upstream. Okay? So when you clamp down those arterioles, arterial blood pressure increases. So this low blood pressure, probably from a low blood volume problem, issue, is solved a little bit in the short term by doing some general vasoconstriction throughout the body. Everything tightens up a little bit and increases arterial pressure, tries to get it back up to normal. Okay? What's the specific effect in the afferent arteriole, which it also targets and causes vasoconstriction in? what's going to happen to the pressure in the glomerulus? Downstream, decrease, right? So you're constricting above, I erased my diagram, but you're constricting the afferent arteriole. That decreases the blood flow going to the glomerulus. Decreased pressure in the glomerulus means decreased or increased GFR. Decreased GFR. If you're low on blood, well, if you're low on pressure, which probably is because you're low on blood, or it could be, you don't want to filter as much fluid. You give the kidney a break, and you don't potentially lose a lot of fluid, and you do that just by slowing down GFR. Okay? Aldosterone. Where does it come from? I know you've done this already, right? It comes from the, give you a hint, it starts with adrenal. Cortex or medulla? Ooh, excellent. Zona glomerulosa of the adrenal cortex. The medulla is the source of epinephrine. Remember, the adrenal cortex on top of the kidney is really two glands, an inside gland that secretes norepinephrine and an outside gland that secretes a lot of things, including the zona glomerulosa, which secretes aldosterone. Okay? Aldosterone is one of the generalized mineralocorticoids. Okay? So it falls under that category. We'll talk about it more as we go along. Okay? There are two stimuli for the release of aldosterone, angiotensin 2, angiotensin 2, which came from renin and which came from low pressure. So low blood pressure ultimately causes angiotensin 2 to go up and aldosterone to go up. Okay? Sorry, aldosterone to go up. So you would say that they work together, right? They're cooperative hormones. They're responding to the same stimulus. In the case of low blood pressure, they are. Okay? But there's a separate stimulus for aldosterone, which is kind of secondary. It has kind of a separate, you got to talk about it a little separately. It's hyperkalemia. What's kalemia? High. What starts with a K that we talk about a lot? Potassium. Okay. High potassium. So if you have elevated potassium, you will also see a stimulus of aldosterone. So think about it this way, and we're going to keep talking about this, especially at the end when I tie it all together. Hyperkalemia causes independently an elevation in aldosterone, but low blood pressure causes both an increase in angiotensin 2 and aldosterone. So I made inference to this complex system that can separate out many different stimuli, which can come together or come separately. High osmolarity generally comes with dehydration along with low blood pressure, but if you eat a ton of salt, you can have high osmolarity and normal blood pressure. Okay? If you eat a ton of potassium, your volume's normal, but you have to deal with the potassium. So we have all these different stimuli, and I'm going to tie it all together for you eventually. Okay? But right now, we're just going to step through this, and we'll see the actual effects of aldosterone on the distal tubules. So targeting a different part of the tubules. The different parts of the tubules are specialized for different things. The distal tubule is clearly responding to aldosterone, whereas angiotensin 2 has a major effect in the proximal tubule. Okay. What do you think aldosterone does to sodium reabsorption? Well, it turns out that it increases it. Okay? If low blood pressure is a potential stimulus for aldosterone, you want to get more salt back in the body, and you want that water to follow it. Okay? What should it do to the rate of potassium reabsorption? If the stimulus is high potassium, you want to reabsorb more potassium? No. And what we'll say here is we'll inhibit potassium reabsorption. We're not actually going to say it causes potassium secretion. Okay? We're going to slow down reabsorption. We're going to let some go. It's already freely filtered, but we're not going to reabsorb as much. We're going to let some go to try to remove this hyperkalemic effect. Stimulus. Okay? Regardless, even though I'm saying you're increasing sodium, you're bringing more sodium into the body, you're letting potassium go, there's still a net, you're reabsorbing more sodium than you're letting potassium go. So there's still a net solute reabsorption, which means if more solutes are absorbed, more water will be reabsorbed. And that makes sense because remember, low blood pressure is one of the potential stimuli for this. Okay? The list continues. Antidiuretic hormone, ADH, aka vasopressin. Okay? Its primary effect is the antidiuretic effect, not as a vasopressor. I prefer the name ADH. You have to recognize both. People still commonly use vasopressin. The stimulus for ADH is high plasma osmolarity. Dehydration, you lose a lot of water, blood gets concentrated, you get a high osmolarity, ADH is secreted. So if we generalize and say dehydration both pressure goes down, volume goes down, pressure goes down, and solutes get concentrated. So now ADH is also going to be secreted. But just understand, and we're going to keep hitting this, it's a different stimulant. Osmolarity versus pressure. They're often the same thing, like in dehydration, they go hand in hand. But if I hemorrhage, is my osmolarity going to go up? No, my volume's going to go down, but my osmolarity won't change. Angiotensin goes up, ADH does not. Okay, we'll hit this later. I just want you to listen. Okay? If I eat a ton of salt, osmolarity goes up, the volume doesn't change. So volume and osmolarity can be tweaked badly independently of each other, though often they go together. Dehydration, all of these are elevated. Angiotensin 2, aldosterone, and ADH are all. So they're, again, cooperative hormones for most situations, most common situations. Okay. Antidiuretic hormone, ADH, where is it secreted from? Excellent. Which part of it? Posterior pituitary. Okay. So the posterior pituitary, oxytocin and ADH. Okay. All the other ones came from the anterior pituitary, except for melatonin, which is the middle, or melanocyte stimulating hormone, which is the middle part. I don't know how you guys broke that down. Okay. The target of ADH is the collecting duct. So the last one, this is the last one in the system, and we'll hit this. This is a very intuitive mean. It causes what happened to the reabsorption of water. Do I want to reabsorb water or let it go? I want to reabsorb it because my plasma osmolarity is high. If nothing else, I'll dilute or try to keep it. Won't actually dilute it. It'll prevent it from getting more concentrated. Okay. But you certainly don't want to let water go if you already have too thick of blood. Okay. Notice I didn't say it causes salt reabsorption and water follows. This is a more direct effect on water alone. Once again, because it's a separate stimulant, it's a plasma osmolarity problem instead of a volume problem. Volume problem, salt plus water gets reabsorbed. Osmolarity problem, only water gets reabsorbed. Do I want to reabsorb salts? Necessarily a lot if I have a high osmolarity. No, right? It's already high. I'm not, now, don't get me wrong, I'm not saying I'm peeing them all away immediately, which I could in 25 minutes. But I'm not going to actively reabsorb them just from the ADH stimulus alone. Okay? And again, I'm going to try to make this clear. I'm sure it's not for most of you yet. Okay? We're going to hit it all again. This is just a preview. Okay? The last one in the suite of the cavalcade of hormones related to the kidney is atrial natriuretic peptide. Okay? If all of these generally battle dehydration, forgetting EPO, we're not talking about EPO anymore. If all these other ones generally battle dehydration, this is the only one that's in the opposite direction. This is the one that's secreted in response to too much volume. Okay? What do you think is the bigger evolutionary pressure? Dehydration or drinking too much? Dehydration. Water is rare. Okay? So we don't have as complex of a system. The bigger the danger, the more complex and beautiful system you'll have. Okay? Elegant. Okay? The less the evolutionary pressure, you might have a single hormone system. So there's a great contrast in what we build to deal with a stress that is not normally encountered, but can encounter. It can happen, and we do see it happen. We do this from also a very strange part. Before the 80s, the heart was not listed under the list of endocrine organs, and now it is, because it secretes this hormone. In response to hypervolemia, too big of a volume, okay, the atria of the heart, literally, you're not emptying the heart as much, it's filling out from the backside, the atria gets stretched. And in response to that stretch receptors sense that stretch and say, you've got too much blood volume, let's secrete some atrial natriuretic peptide. And what does natriuresis mean? Does anybody know? What does diuresis mean? Water loss. We'll talk about, I'll define that for you later. Okay? Natriuresis thus means salt loss. You're dumping salt. It causes natriuresis. If you cause salt to be lost, what follows salt? Water. You dump plasma. You dump salt water. That's the main effect. It's more complex than that, it turns out, but that's where the name originates from. Okay? It targets the kidney, so it's secreted from the heart now, and targets the kidney. It inhibits distal tubule, so it's going to target the distal tubule, sodium reabsorption, we'll talk about that later. Okay? And if it inhibits sodium reabsorption, that salt isn't reabsorbed and water doesn't follow it, salt water gets peed away. Okay? It inhibits renin, thus angiotensin II. It inhibits renin directly, and angiotensin II thus indirectly, and aldosterone indirectly. Because angiotensin is a stimulus for aldosterone secretion, inhibit angiotensin II, inhibit aldosterone secretion. These act to conserve volume. Clearly you want to inhibit that conservation of volume and dump their effects on conserving volume and lose volume. Okay? It has some subtle effects on arterioles. If you vasodilate the arterioles, what happens to your arterial blood pressure? It drops. Okay? And that's good because too much volume causes a momentary increase in high blood pressure, and that's chronically dangerous, but in the short term it's bad too. In the afferent arteriole specifically, it also inhibits that one and causes vasodilation of the afferent arteriole. What does that do to GFR? Increases it, right? Just the opposite of before, right? If you vasoconstrict the afferent arteriole, you decrease GFR. If you vasodilate the afferent arteriole, you increase the capillary pressure within the glomerulus, you increase the glomerular filtration rate. Okay? With me? Hit all of these again as we see what they target. We'll talk about the targets of them. So we then move on to part F, which is the tubules themselves. Okay? So now we start a long process of stepping through the tubules and looking at their individual functions. We generalize their functions. Okay? Our general diagram includes, again, the glomerulus, the capsule, and then we'll have the proximal tubule first. Okay? We'll have the descending loop of Henle and the ascending loop of Henle. The descending loop of Henle is primarily thin. The ascending loop is primarily thick. Okay? So I generally abbreviate them, sorry. The descending loop, fluids going this direction, and the ascending loop, fluids going this direction. Okay? We have the distal tubule, and then we have the collecting duct. Okay? So we'll start with the proximal tubule. Now, just relative to this general picture, when you look at a good diagram in your book, you'll see that generally this occurs in the cortex, and this, not generally, it does. And this occurs in the medulla. What we're saying is that the loop dips down into the medulla and comes back to the cortex. And eventually the collecting duct goes through the medulla, the center of the kidney. Okay? So the morphological arrangement of the kidney, when you think about it, okay, has the cortex on the outside. It's got all these renal corpuscles with the glomeruli, okay, all throughout here. And it's got these loops and collecting ducts. Loop and collecting duct. Loop and collecting duct. And all these collecting ducts come together to form the ureter or urethra. Good job. Okay. So first, part one under the tubules is the proximal tubule. The proximal and distal tubules are also called the proximal convoluted tubule and the distal convoluted tubules because they wind around like this. They're not straight like I'm drawing there. Okay? I just abbreviate them as proximal and distal, which many others do too. You'll see the convoluted nature of it when you look at them histologically in the lab. Okay? Proximal tubule. If you have to guess where something happens, it happens in the proximal tubule. This is where the action goes on. It has the first shot at the filtrate, and it does a lot to the filtrate. So there's a lot of action in here. And when you look at the cells of the proximal tubule in histology, you'll see they have a big, thick brush border, lots of surface area to act upon and to put receptors and transport pumps, and not receptors, transport pumps on. Okay? You'll see that the cells here look very dark compared to a lot of the tubules, and that's because there's a lot of mitochondria and a lot of machinery within here. Okay? They're thick, they're full of machines that are pumping things and growing things and building protein. Okay? They just tend to stain darker. Okay? And in contrast to the proximal and the distal next to it, you'll see that very good contrast between the two. Okay? So lots of action going on in the proximal tubule. That's the first thing you want to know. Reabsorption, a ton of reabsorption takes place in the proximal tubule. Okay? The majority of reabsorption occurs here. Okay? So the microvilli are a surface area phenomenon. You did digest them already? Yes? You saw the microvilli with increased surface area for absorption. A lot of them in the duodenum and throughout the small intestine where most of the absorption takes place. Same kind of idea here. Okay, so when I draw these tubules, okay, and I draw the mechanisms for them, I'm going to draw them like this over and over again. And what I'm indicating is one of these cells, and I put a little curve on it to indicate the lumen on this side. Okay, this surface would be referred to as the apical surface. Remember, it's an epithelium. It has a free surface. Okay, this side over here would be referred to as the basal or the basolateral. Okay, and what you should understand about epithelia is the characteristics of this side of the cell can differ dramatically from the characteristics on this side of the cell. And the first thing you're always going to draw on all these cells is your old friend, the sodium potassium ATPase. Okay? Because it is the driver of almost everything we'll talk about from here on out. Okay? Which way is it pumping sodium? This way or this way? Out of the cell or into the cell? Sodium's high outside the cell, low inside the cell. It's always maintaining that. Okay? And it's pumping potassium into the cell. Okay? It uses ATP, which is more of 3 sodium or 3 potassium. I always have to think through it because I never remember the default answer. My answer is it's more negative inside the cell, right? And it is outside the cell, negative. The membrane potential still exists here, even though there's no action potential. Okay? And if I put 3 sodiums out here and only put 2 inside, that creates a more negative. So I can always remember from that little logic, which actually isn't really true. It doesn't drive the membrane potential into itself that way. Permeability drives the membrane potential more than anything else. But nevertheless, it works for me. I always remember 3 go out and 2 go in. Okay? Make it more relatively negative inside. Okay? So, the first example we'll talk about in here is glucose uptake. Okay? And by that I mean glucose reabsorption. Looking at my notes and I'm remembering a magic number to tell you, which you don't have to know, but it is impressive. Sodium potassium ATPase drives everything. Okay? The number I found somewhere, which I forget where I found it, but I believed it at the time, so I must have been a reasonable source, is within every glomerulus, the tubule has these sodium potassium ATPases throughout it. Okay? 66 trillion turns or motions per second per nephron. So take 66 trillion and multiply it per second by about 2 million nephrons within both of the kidneys, and then multiply that by 60 to get a minute, 60 by an hour, and you come up with some really big numbers. So again, those numbers just always impress me. I never fail to be amazed by how many molecules there are that are being pumped around. And remember the amount of filtrate that's coming down this thing, this tube, right? You need a lot. Most of the stuff gets reabsorbed, and it's a lot of fluid. So, it might be a surprising number, but that it's a big number isn't surprising at all. 66 trillion times per second, 1 nephron. Pretty crazy. Anyway, we use glucose reabsorption as our first example, and like almost everything we'll talk about is driven by the sodium potassium ATPase. Okay? And so what we do is we have a co-transporter here, okay, which has the movement of glucose in from the filtrate. Remember, it's freely filtered in the glomerulus, nothing holding it back, and we need to get that glucose back. Okay? It gets pulled in with sodium co-transporter. Okay? So what kind of categorical name do I give to this? Active or passive? Active transport, ATPs. Or things are moving against their gradient. That's the better thing for active. Okay? Primary or secondary? Primary active transport uses ATP directly to pump things against their gradient. Okay? Is sodium going down its gradient? Is it going downhill or uphill? Downhill. Good. It's going downhill because sodium's being pulled out. We're keeping it low in here and we're pulling it in. Okay? But glucose, you have to picture and believe that this has been happening for a while. And glucose is going uphill. Okay? Glucose has a hard time getting into this cell. And only kind of a chicken or egg question. If we pumped a bunch of glucose in, then it's hard to get in, right? So we need secondary active transport. So this is the secondary active transport. Okay? Doesn't use ATP directly, but glucose is going against its gradient. Okay? Sodium's not Not all the ions involved in secondary active transport are going into gradient, but if one is, it's secondary active transport. It's secondary active transport. Okay? And the reason why I know it's high in here is because there's another mechanism here that glucose then goes in and is completely reabsorbed. Okay? The first step, get it into the cell, the tubular cell. Second step, get it back into the interstitium. And then from there, of course, glucose can go into the paratubular capillaries and be reabsorbed back into the bloodstream where it came from and where we want to keep it. Okay? So glucose comes in here. I know it's high here, and I can use that because it moves downhill here. Okay? So if this is moving downhill, what do we call this? Diffusion or active? Simple or facilitated? Facilitated. Yeah. If you built a pore for glucose to go through, what would happen? It would be so gigantic that everything else would equilibrate as well, and we lose our sodium and potassium and chloride and calcium ingredients. Okay? So we can't have a pore for glucose. It's too big. We have to have a molecule, a protein that it binds to and is translocated across the membrane, but it's still going downhill. It's still the gradient is the energy that causes that thing, when it binds, to flip it over and push it to the other side. So facilitated diffusion. Okay? There are some examples of simple diffusion. For example, there is a pore that's free to potassium, and potassium movement is essentially inconsequential. It gets pumped back in by the sodium, potassium, ATPase, but that's not the point of this. The point is to get sodium out, to get sodium to pull glucose in with it. Right? Potassium gets pumped in and it just flows right back out through an open pore. Okay? This is simple diffusion. You'll be required to know this example in detail. Okay? Reproduce it, fill it in, whatever. The good news is it's pretty much the exact same for amino acids. You have a supply of amino acids in your bloodstream. They're small little molecules that are freely filtered. They're good things, and always good things. You'll never try to pee away amino acids or glucose. Try to, I said. You will always try to reabsorb them completely. And the proximal tubule will reabsorb all of them completely under normal conditions. So much so that there aren't even any glucose transporters downstream from the proximal tubule. They're very dense. And with the normal blood sugar of 90 mg per mil, you'll get complete reabsorption. But my last point is to illustrate another important thing about these transport mechanisms we're discussing. There's only so many of these, and there's only so many of these. There's only so many. You can saturate them. Okay? If you have too high of a blood sugar, your kidney's not built to pull in that much glucose because it's freely filtered still. And if your blood glucose is 200, they're going to get into your proximal tubule. They're going to get past the glucose transporters because you've saturated them. All the ones are busy and the glucose snuck by and you pee it away. The sugar in your urine is a reflection of hyperglycemia. What is hyperglycemia often a reflection of? It occurs during diabetes. Okay? Whether diabetes mellitus or diabetes insipidus. Back before we had good assays, the doctor would have you pee in a cup, you'd taste the pee, you'd taste the pee, you would say, ooh, that's sweet. You have diabetes. Okay? And so it illustrates the saturation characteristics. Everything we're going to talk about is saturatable. Okay? When you have enzymes and a process to convert something to something else, there's only so many enzymes. You can saturate those enzymes and you have a limit to how fast the reaction can ultimately occur. And same thing for reabsorption. You have a limit to how fast reabsorption can actually occur. Okay? And if you're hyperglycemic, you can get over, you can saturate those and you can lose them. Remember, there's no backup glucose transporters downstream, so you just pee it away. Okay? Make sense? Good. We'll continue on from there with a couple more examples from the proximal tubule. and talking about how Angie attempted to target the proximal tubule coming up next. Yeah,
That's where you're supposed to be shot.
I didn't know.
Gives it ease steps.
figure it out.
My dad.
Good, I like it. Remind me what to do.
Correct. Really use it. Forget about it until next time I can find something.
I live on Upward Drive.